Our universe is a vast and enigmatic expanse, full of mysteries that have captivated humankind for millennia. One of the most profound puzzles in cosmology is the nature of the cosmological constant, a concept that has revolutionized our understanding of the cosmos. This constant, denoted by the Greek letter lambda, represents a fundamental property of space itself, an inherent energy that pervades the fabric of the universe. The cosmological constant plays a pivotal role in determining the fate of the universe, influencing whether it will expand forever, slow down, or eventually collapse upon itself. Its presence or absence has profound implications for the very structure of space-time, shaping the cosmic landscape on the grandest scales. The value of the cosmological constant is incredibly small, yet its impact is immeasurable. Join me as we delve into the fascinating world of the cosmological constant, exploring its history, its significance, and the profound implications it holds for our understanding of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his groundbreaking theory of general relativity. Einstein's equations painted a picture of a dynamic universe, where gravity was not a force but rather a curvature in the fabric of space-time. However, at the time, the prevailing scientific belief was that the universe was static and unchanging. To reconcile his equations with the prevailing view, Einstein introduced the cosmological constant as a fudge factor. He envisioned this constant as a repulsive force that counteracted the inward pull of gravity, thus maintaining a static universe. This addition, while seemingly elegant, was driven more by philosophical preference than by observational evidence. In 1929, Edwin Hubble made a groundbreaking discovery that would forever change our view of the cosmos. Hubble observed that distant galaxies were receding from us, and the farther away they were, the faster they seemed to be moving. This observation indicated that the universe was not static but rather expanding. With the discovery of the expanding universe, the need for a cosmological constant to maintain a static cosmos evaporated. To fully grasp the significance of the cosmological constant, we must delve into the heart of Einstein's theory of general relativity. This groundbreaking theory describes gravity not as a force acting at a distance, but rather as a consequence of the curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. Similarly, massive objects in space warp the fabric of space-time, influencing the motion of other objects around them. The cosmological constant, represented by lambda, appears as an additional term in these equations. This term can be interpreted as an inherent energy density associated with the vacuum of space itself, a kind of energy that exists even in the absence of matter or radiation. Depending on its value, the cosmological constant can either counteract the attractive force of gravity, causing the expansion of the universe to accelerate, or it can contribute to the gravitational pull, potentially leading to a future collapse of the cosmos. Its presence in the equations of general relativity continues to shape our understanding of the cosmos and drive ongoing research into the fundamental nature of the universe. The discovery of the expanding universe in the early 20th century marked a turning point in cosmology, challenging the long-held belief in a static cosmos. Edwin Hubble's observations of receding galaxies provided compelling evidence that the universe was not immutable, but rather engaged in a continuous process of expansion. This discovery revolutionized our understanding of the cosmos and paved the way for the development of the Big Bang theory. As astronomers continued to probe the depths of space, they made another startling discovery in the late 1990s. Observations of distant supernovae revealed that the expansion of the universe was not slowing down as expected due to gravity, but rather accelerating. This unexpected finding sent shockwaves through the scientific community, forcing cosmologists to reevaluate their models of the universe. To account for this perplexing phenomenon, scientists resurrected Einstein's long-discarded cosmological constant. The cosmological constant, once considered a blunder, had become a crucial component in our understanding of the cosmos. The accelerated expansion of the universe is a profound mystery that has captivated cosmologists for decades. Scientists introduced dark energy, a hypothetical form of energy that permeates all of space and exerts a negative pressure, counteracting gravity. Dark energy constitutes roughly 68% of the universe's total energy density. The cosmological constant, denoted by lambda, is the simplest model for dark energy. In this model, dark energy is a constant energy density, inherent to space itself. As space expands, dark energy increases, accelerating the expansion further. Despite its success, the nature and origin of dark energy remain elusive. Scientists are actively pursuing various research avenues to unravel its mysteries. The quest to understand dark energy is one of the most exciting frontiers in modern physics and cosmology. The value of the cosmological constant has profound implications for the ultimate fate of the universe. A positive cosmological constant, as currently observed, leads to an accelerated expansion, suggesting that the universe will continue to expand forever. In this scenario, known as the Big Freeze, galaxies will drift farther and farther apart, and the universe will become increasingly cold and dark as stars eventually exhaust their nuclear fuel. If the cosmological constant were to be negative, the expansion of the universe would eventually halt, and gravity would take over, pulling everything back together in a cataclysmic event known as the Big Crunch. However, current observations strongly favor a positive cosmological constant, making the Big Crunch scenario highly unlikely. The precise value of the cosmological constant also determines the geometry of the universe. A positive cosmological constant leads to a flat universe where parallel lines remain parallel, while a negative cosmological constant would result in a closed universe, where parallel lines eventually intersect. Observations suggest that our universe is remarkably close to being flat, further supporting the idea of a positive cosmological constant. Understanding the nature and evolution of the cosmological constant is essential for unraveling the ultimate destiny of the universe and our place within it. Measuring the cosmological constant is a formidable challenge. Its influence is subtle and only becomes apparent on vast cosmic scales. Astronomers have devised ingenious methods to measure this elusive constant, primarily relying on observations of distant objects and phenomena that are sensitive to the expansion history of the universe. One of the primary methods for measuring the cosmological constant involves observing type Ia supernovae. These stellar explosions serve as standard candles because they have a known intrinsic brightness. By measuring the apparent brightness of distant type Ia supernovae, astronomers can determine their distances and, consequently, how much the universe has expanded since the light from these explosions was emitted. These measurements have provided compelling evidence for the accelerated expansion of the universe and have been instrumental in constraining the value of the cosmological constant. Another approach involves studying the cosmic microwave background, or CMB radiation, the faint afterglow of the Big Bang. By combining data from various cosmological probes, such as supernovae, the CMB, and baryon acoustic oscillations, astronomers have been able to determine the value of the cosmological constant with remarkable precision. The current best estimate suggests that the cosmological constant is extremely small but positive, consistent with a universe that is expanding at an accelerating rate. While the cosmological constant explains the universe's accelerated expansion, it faces significant challenges. Theoretical calculations predict a much larger value than observed, leading to the cosmological constant problem. This discrepancy has led to alternative theories like FR, gravity, and quintessence. The coincidence problem also challenges the cosmological constant model. Scientists continue to explore and refine measurements to solve this mystery. The cosmological constant stands as a testament to the ever-evolving nature of our understanding of the universe. What was once considered a blunder by Einstein has become a cornerstone of modern cosmology, providing a framework for comprehending the enigmatic phenomenon of the accelerated expansion of the universe. However, the quest to fully unravel the mysteries of the cosmological constant is far from over. Advances in observational astronomy, such as the launch of the James Webb Space Telescope, promise to provide unprecedented data that will further constrain models of dark energy and the evolution of the cosmos. As we continue to explore the cosmos and probe the fundamental laws of physics, we can expect to uncover even more surprises and deepen our understanding of the universe and our place within it. The journey of scientific exploration is an ongoing adventure, and the cosmological constant will undoubtedly continue to play a central role in shaping our understanding of the cosmos for generations to come.